Introduce solar radiation through fenestration, define solar heat gain factor and shading coefficient, discuss effects of external shading, introduce ventilation and infiltration, and discuss estimation of heating and cooling loads due to ventilation and infiltration. So, at the end of the lecture you should be able to estimate heat transmitted into a building due to solar radiation through fenestration using values of solar heat gain factor and shading coefficient from tables, calculate dimensions of the overhangs for external shading, explain the importance of ventilation, and estimate heating and cooling loads due to ventilation and infiltration. Before that, let me just work out an example on calculation of solar radiation on a south facing wall. The example is like this: you have to calculate the total solar radiation incident on a south facing vertical surface at solar noon on June 21st and December 21st using the data given below. The latitude angle is given to be 23 degrees centigrade and the hour angle is 0 degrees because it is at solar noon. Okay, this is not given, but you have to infer this from the given information. And the declination is plus 23.5 degrees on June 21st and minus 23.5 degrees on December 21st. And the tilt angle here is 90 degrees because it is a vertical surface. And the wall azimuth angle zeta is 0 degrees centigrade because the wall is south facing. And finally, it is given that the reflectivity of the ground is 0.6. So, this is the information given and based on this we will have to calculate the total solar radiation. Okay, so here a stepwise procedure is shown. First what we do is we find out the altitude angle beta. Since we are doing the calculations at solar noon, the beta is nothing but beta max, that is given by pi by 2 minus absolute value of L minus D, where L is the latitude and D is the declination. So, you find that the altitude angle works out to be 89.53 degrees. First I am doing the calculation for June 21st. Okay, so here I take the declination as 23.5 degrees. Next, at solar noon we have to calculate what is the solar azimuth angle. Since we are making the calculations at solar noon, the solar azimuth angle is either 180 degrees or 0 degrees. It is 0 degrees if latitude is less than declination. So, you have to take solar azimuth angle to be 0 degrees in this case. Okay. And next we have to calculate what is wall solar azimuth angle alpha. The wall solar azimuth angle alpha is given by 180 minus gamma plus zeta, and here you find that gamma is 0 and zeta is also 0. So, you find that the value of alpha is 180 degrees for this particular case. Okay, once you know the value of alpha and the value of beta, we can calculate the incidence angle. Since this is a vertical wall, the incidence angle is given by theta vertical is cos inverse cos beta into cos alpha. Beta is 89.53 degrees and alpha is 180 degrees. So, from this you find that the incidence angle is 89.53 degrees. Once you know the incident angle, we can calculate what is the direct radiation on the surface. The direct radiation is given by IDN cos theta. So, first let us find out IDN. From the ASHRAE model, IDN is given by A multiplied by exponential within bracket minus B by sin beta, where beta is altitude angle, that is 89.53 degrees, and A is 1080 for summer. So, you take the value of A as 1080 and B, which is called as the extinction coefficient, it takes a value of 0.21 for summer. These aspects I have discussed in the last lecture. Okay. So, you take these values of 1080 for A and 0.21 for B and substitute the value of beta, you find that the direct normal radiation is 875.4 watt per meter square. So, we have to find out what is the direct radiation on the vertical surface. So, that you have to find out by multiplying this with cos theta, where theta is the angle of incident. Okay, that is the 89.53 degrees. So, if you find that, you will find that IDN cos theta works out to be 7.18 watt per meter square. Okay. Next, we have to find out the diffuse radiation. Diffuse radiation, for that we have to find out the view factor. View factor is given by 1 plus cos epsilon by 2, and this is 90 degrees. So, you find the view factor is 0.5. Okay, this is for the diffuse radiation. Once you know the view factor, diffuse radiation given by, again based on the ASHRAE model, ID is equal to C into I subscript Dn into F subscript Ws, where C takes a value of 0.135 for summer. Since I am making the calculations for June, I take a value of 0.135 and IDN works out to be 875.4 as shown in the last slide, and FWS is 0.5. So, if you substitute all these values, you find that the diffuse radiation is 59.1 watt per meter square. Next, we have to find out the reflected radiation. Reflected radiation also has a view factor between the ground and the wall. So, first let us find the view factor between the ground and the wall, that is F subscript WZ, this one, that is given by 1 minus cos epsilon by 2. So, this works out to be 0.5. Then based on the ASHRAE model, the reflected radiation from the ground is equal to IDN plus I diffuse multiplied by rho z into FWZ, where rho z is the reflectivity of the ground, which is given as 0.6, and FWZ is 0.5. So, if you substitute the value of IDN and I diffuse, you find that the reflected radiation works out to be 280.36 watt per meter square. So, the total incident radiation is nothing but sum total of direct radiation contribution, diffuse radiation and reflected radiation. So, the direct radiation, total radiation works out to be 346.64 watt per meter square. Okay, so, this is a fairly straightforward procedure. This is for a vertical wall. If the surface is inclined, then you have to use the tilt angle, and if it is facing any other direction other than south, then you have to use proper surface azimuth angle, okay, as explained in the last lecture. In the same manner, you can calculate all these parameters for December 21st. Okay, for December 21st, the declination angle will be minus 23.5 degrees. Okay, so now let me show a table where the solar radiation results for June 21st and December 21st are given. So, this table shows the comparison between June 21st and December 21st. June 21st, you find that the incidence angle is 89.53, whereas for December 21st it is 43.53. The direct radiation IDN is 875.4 watt per meter square in case of June 21st, and it is 1003.75 in case of December. Similarly, the contribution of direct radiation is nothing but IDN cos theta is 7.18 watt per meter square for June and 727.7 watt per meter square for December. Okay, and the diffuse radiation is 59.1 and 29.1, and reflected radiation is 280.36 and 39.9 in case of December. So, the total incident radiation on the vertical surface is 346.64 watt per meter square on June 21st and 1066.7 watt per meter square on December 21st. Okay. This example actually gives us some useful information. That information is that this is a south facing wall. You observe here that for south facing wall, if you get the total radiation incident on the wall is 346.64 watt per meter square in summer, whereas it is almost 1100 watt per meter square in winter. Okay, and here for summer, this value is coming because of the reflected radiation, because we have taken 0.6 as the reflectivity of the ground. If the ground is not so reflective, you find that the total incident radiation on the vertical surface on June will be very small, whereas it is very high on the on December 21st, or that is in winter. Okay, so this tells us this gives us an important information, that is that for south facing walls, the solar radiation incident on a vertical surface is much less in June, whereas it is much higher in winter. Okay. So, since we want to reduce the load, heat load on the building during summer, and we want to maximize the heat transfer to the building during winter, it is always beneficial to keep windows, doors, etc. on south side. Okay, so that the radiation part will be small in summer and it will be large in winter. So, your cooling capacity requirement will be small and the heating capacity requirement also will be small. Okay, so this is a principle generally used in passive cooling and heating techniques. Okay, use the south wall properly, and of course these results hold good for northern hemisphere. Okay, because the latitude is 23 degree north. The results will be different if we are talking about southern hemisphere. Okay. And so far this ASHRAE model, in fact if you remember, I have mentioned in the last class that this model assumes that the sky is cloudless. Okay, but if the sky is cloudy, sometimes what is done is a clearness index value is used to calculate the incident direct solar radiation. Okay, the clearness index value is 1 if the sky is clear, and it will be less than 1 if the sky is cloudy. Okay, and the clearness index value for different regions during different seasons are available. Okay, so from that data you can calculate what is the radiation during a cloudy day. Okay. Now next let us look at solar radiation through fenestration. First of all, what is fenestration? Fenestration refers to any glazed apertures in a building such as glass doors, windows, skylights, etc. That means it refers to all those transparent surfaces such as doors, windows, skylights, etc. Okay, all these are called as fenestration. We need fenestration, all buildings have fenestration. Why do we need fenestration? It is required because it provides daylight, heat and outside air, and fenestration also provides visual communication to the outside world. It also improves aesthetics, and finally it provides an escape route in case of fires in low rise buildings. Because of all these factors, almost all buildings will have some amount of fenestration. That means you will have some amount of glass windows or glass doors, etc. Okay, because of the 4 reasons mentioned here. Now let us see what is the effect of this on the cooling and heating loads. Heat transfer due to solar radiation through transparent surfaces is distinctly different from heat transfer through opaque surfaces. This is one important thing to note. Okay, what is the difference? Radiation incident on an opaque surface, for example a wall or a roof, is partly absorbed and the remaining is reflected back. Because it is opaque surface, so its transmittivity is 0. So whatever radiation is incident, either it is absorbed or it is reflected. That means it is partly absorbed and partly reflected. And out of the absorbed part, only a fraction of it is transferred into the building. This aspect we will discuss in the next lecture. So ultimately, whenever radiation is incident on an opaque building, some of it is absorbed and some of it is reflected back, and out of the absorbed portion only a part is finally transferred to the building. That means only a part of the radiation incident on an opaque surface finally becomes a load on the building. Okay, this is as far as the opaque surface is concerned. Now let us look at a transparent surface. For a transparent surface, a major part of the radiation incident on a transparent surface is directly transmitted into the building, while the rest is absorbed and reflected back. We know this from our basic physics that all transparent surfaces have high transmittivity. Okay, so whenever radiation is incident on the surface, most of it is transmitted through the surface, right? Transmitted through the glass, and only a small part of it is absorbed and a small part of it is reflected back. So this is the major difference between the transparent surface and opaque surface, and this has a huge effect on the heating and cooling loads. Okay, first let us look at a reference surface and see what happens to the radiation. Okay, this is a distribution of solar radiation on a clear plate glass. Okay, for a clear plate glass. Clear plate glass has these optical properties. It has a transmittivity of 0.8, it has an absorptivity of 0.12, it has a reflectivity of 0.08. Okay, so these are the values for the solar radiation. For solar radiation, these are the values. Now, since it has a transmittivity of 0.8, if 100% of solar radiation is incident on this window, okay, which is nothing but your window made of clear plate glass, 80% of it is directly transmitted to the indoors, okay, because it has a transmittivity of 0.8, right, and 12% of it is absorbed by the glass, while 8% of it is reflected back. Okay, this is based on the optical properties of the clear glass. Now, of the 12% absorbed, what happens to this 12% of the radiation absorbed by the glass? This will increase the temperature of the glass. That means glass temperature increases due to absorption. Okay, absorption of radiation. Right. So once the glass temperature increases, it rejects some heat by convection to the outside, and some part of it is rejected to the indoors. Okay. So for example, typical values are this particular glass will reject about 8% to the outside and about 4% to the indoors. So finally, you see that out of the 100% solar radiation incident on the surface, 80% plus 4%, that is 84% is directly transmitted to the building or to the indoors, while 16% is transmitted to the outside. Okay. This is for a clear plate glass, and these values will be different for different types of glasses. Okay. Now, what is the importance of fenestration on glazed surfaces? Why do we have to consider this seriously? Fenestration or glazed surfaces contribute a major part of cooling load of a building. Okay, so the energy transfer due to fenestration depends on the characteristics of the surface and its orientation, weather and solar radiation conditions. So, careful design of fenestration can reduce the building energy consumption considerably. Okay, so if you design it properly, then fenestration can help you in reducing the initial and running costs. But if you don't design it properly, then you will have to pay both in terms of initial and running costs. For example, if you design the fenestration properly, that means if you put the glass, windows, doors, etc. Properly on proper direction and with a proper orientation, you will find that the radiation transmitted to the building during summer can be reduced very much, whereas it can be increased very much in winter. As a result, the cooling load on the building can be reduced during summer and the heating load on the building can be reduced in winter. Okay, so the required cooling and heating capacities will be less, so your initial and running costs will be less. Okay, so if you are if you are using the fenestration properly. Okay, instead of that, if you are putting glass left and right just to increase the aesthetics or anything, you will find that both heating as well as cooling loads will increase. Okay, so ultimately you will have to pay for this in terms of initial and running costs. Okay, so that's why it is very important to understand the importance of fenestration and the issues involved in the design of fenestration for buildings. Now, let us look at a simple model for calculating solar radiation passing through a transparent surface. Okay, so this model is based on these assumptions. The assumptions are like this. So this is valid under the assumption that the transmittivity, that is the tau value, and absorptivity, that is alpha value, of the fenestration is same for both direct as well as diffuse radiation. This is an important point to be remembered. In actual case, you find that the transmittivity and absorptivity of the glass will be different for direct radiation and diffuse radiation. Okay, the values will be different, and the transmittivity and absorptivity values of direct radiation, okay, it depends strongly on the angle of incidence, right. So this is again a very important point to be remembered. The transmittivity and absorptivity of the glass for direct radiation is not a constant. Okay, so it is a function of the angle of incidence, and as we have seen, the angle of incidence itself varies. It varies with the latitude, it varies with hour angle, it varies with the declination and with the orientation, etc. Right. So based on this, the transmittivity and absorptivity of the glass also varies, whereas the transmittivity and absorptivity of the diffuse radiation remains more or less constant. Okay. However, the model that I am going to present, which is taken actually from ASHRAE handbooks, it is based on the assumption that the transmittivity and absorptivity values are same, are constant, and they are same for both direct radiation as well as diffuse radiation. However, this assumption is justified because normally we do the calculations for the peak load conditions. Okay, and at peak load conditions you find that the contribution of direct radiation is much larger compared to the diffuse radiation. I am sorry. So direct radiation is much larger than the diffuse radiation. So if you are assuming that the tau values and alpha values are same for both, you won't be making a huge error. Okay, and besides it simplifies the procedure. However, it is not necessary that you have to assume them to be same. Okay, with a little bit of extension, you can take different values of tau and alpha for diffuse radiation and direct radiation and do the calculation separately. Okay. So under this assumption, you can write the solar radiation transmitted to the building Q subscript Sg, okay, is equal to A multiplied by within brackets tau into I subscript T plus N multiplied by alpha multiplied by I subscript T. Here as I said, QSG, okay, is the radiation transmitted to the building and the units are watts in SI units, okay, and A is the area of the surface exposed to radiation in meter square. IT is the total radiation incident on the surface. So this includes both direct plus diffuse. Okay, of course you can also include reflected radiation. Normally reflected radiation will be a small part. So, this includes the total radiation incident on the surface, and tau is, as you know, is the transmittivity of the glass, alpha is the absorptivity of the glass. And what is n? N is a new parameter, and this is the fraction of absorbed radiation transferred to the indoors by conduction and convection. In fact, I was mentioning that when the glass absorbs radiation, its temperature increases. So, because of the temperature difference between the glass and the surroundings,